So the roof of this particular project, the roof assembly is basically a simple mono truss package. Cheap, quick, easy, simple. We actually ended up blowing about 30 inches of cellulose into the attic, so this R value is not exact, but it's pretty close. It's about as simple as you can get. I'm of the opinion now that our 86 roof is a little bit wimpy. You can see here's a detail of the eave detail with a traditional raised heel for the mono truss to allow for thermal bridge free installation of the insulation. Here's a portion of the cellulose that we use to insulate this home. We're right around 400 or so bags per house, depending on the size of the house and the volume-ish. Our values of the wall assembly in PHPP is our 58.6. We only took a 5% reduction for the volume of lumber in the assembly. The wall assembly from outside to in, from inside to out rather, gypsum, mineral wool, 2x4, exterior load-bearing wall, point-loaded to the trusses. OSB is our air barrier, and we ran 11 7/8 TJIs, basically strapped the entire house with TJIs and dense packed those with cellulose. And then the fiber sheathing, which is a high perm product from Canada, BH900, which I'll talk about that a little bit more later. Window header details, again, you can see the interior load-bearing wall. The major consideration for this project was trying to get this thermal bridge free as possible, and we did achieve that. Here's a picture of the wall assembly during construction. We primed all of the joints, all of the seams with exterior latex primer, applied gray slide core to all the joints as an air sealing strategy. At that time, I was extremely paranoid about the penetrations. We used 5/16 by 4-inch GRK lags, which is all we use in GRK fasteners. I was very concerned about penetrating the 3M tape with the screws. I felt like the bicore, although it was not as sticky, had better sealability characteristics. I'm less concerned of that now. I'm also a little bit less paranoid about the air tightness and trying to build a house and fail, which was a big fear of mine going into this project, having never built one before. As you can see, it's not that complicated. This is the wall framing system. It's not that complicated of a system, but we actually took a couple extra steps to decrease the thermal bridging. That window buck that you see is fastened to the interior 2x4 load-bearing wall, and then we actually notched out underneath this window buck, so we put another piece of engineered lumber in there to separate the plate for the window installation. This also allows us to set foam on the other side of this and completely thermally break this and the window. The window is installed, gets set in the center of the thermal envelope, and it is installed flush with that window buck, allowing us to take the window buck back to the OSB and take the exterior of the window frame directly to the face of the window buck, and you get good adhesion, good air tightness. It's a little bit complex from a framing detail, but we have saws and tools and tape measures, and it can be accomplished fairly easily in the field by decent carpenters. Here's an example of the thermally broken window buck. You can see the second layer is set up from that and fits into the rabbet on the end of the TJI. Another picture of the window installation. I don't know if this shows, no, this is after all of that stuff. Windows in place, foamed in, weather barriers applied, rain screen is applied. This view value of the windows, 0.14. They are not Passive House certified windows. I did not want to use a window that was Passive House certified. I didn't want to pay the premium for that product and for the certification, so we sought out windows that met the Passive House metrics, felt like they would meet the quality standards that we were trying to achieve, but without the price point. We ended up going with a company called Intus Windows. We've been pretty happy with their products, and we've installed them in 4 projects to date with pretty good success. They're vinyl windows, UPVC windows. They are not the sexiest windows, but they perform pretty well. Mechanicals, we chose a Zender 200 Pumpo Air 200. This is a fantastic performing device. It's 92% efficient. I believe it's about 0.25 watts per CFM. And the flow rate in this house is about 74, I think 75 CFM. It's a relatively small house. The entire house is heated with a single air source heat pump, Mitsubishi mini split, MUZ FE12NA condenser and the evaporator. It's a 1-ton, 12,000 BTU unit. For the most part during construction, we didn't have any heat in the home until about the end of December, and the house was staying a pretty consistent 57, 55, 56, 57, 58, in that range with just the solar heat gain from the windows and no gain from thermal mass in the floors since they were covered. Thermal bridging, I feel like, is a very understated component of Passive House design. It is so important, and it's a very easy way to gain free heat from these buildings, as long as it's implemented well. So, what? And these are the thermal bridging calculations for this particular project. As you can see, they're all negative with the exception of the window installation. This was modeled using a program called Therm. And here is some cool pictures of isotherms and a spreadsheet from the thermal bridging analysis. This is the roof to wall connection. This actually is not the connection for this house. It's a similar connection using a scissor truss that we modeled just to give you kind of an idea of where we're at. And we're at negative 0.019 for a psi value at that connection. Same with the outside corners, negative. Window installation, 0.003, that is probably the jams to say on here. Anyways, it's very low. It's pretty thermally neutral, and that's about, I think, as low as you can get with the window installation. I have not yet seen any negative thermal bridging at a window installation, so if anybody has figured out how to do that, I'd like to get plugged into that. Thermal bridging, and air tightness, the last major component. We blower door tested this house about 7 or 8 times throughout the construction process. I wish I had the capacity to blower door test the envelope versus the windows. We just didn't have that capacity. And we have not tried to do that since, although we should. 11,183 cubic feet in this house. It has a TFA of about 1140 and gross square footage is 1,600. So that's the volume based on the EIN standard. We were at 50.6 pascals and 53 CFM, which is extremely low. After the project, this was the best blower door test that we had on this particular project. At the end of the project, we had climbed back up to about just under 0.4, 0.38 ACH 50, which is still pretty good. But after the installation of the cellulose and after the rest of the construction, the rest of the penetrations and all that stuff that took place post that particular blower door, we did climb back up again. And that pretty much covers the Knox house. The next project that I want to talk about is called Charlotte's Retro. This is a 1965 cape. It had a great foundation, perfectly dry basement, and a little bit of personal history. This is my family's personal home. It's been in my wife's family for 25 years. It was their summer home for years and years. My wife spent her summers in this house growing up as a child. Her mother, Charlotte, passed away about 7 or 8 years ago, and we're never going to get rid of this house, ever. So this is a little bit of a condensed version. The house is actually scaled a little bit differently than that. But you can see this is where we were beginning from in terms of a deep energy retrofit project. This house, we were trying to get as close to passive house as we could without having any preconceived notions of actually meeting the standard. We were always trying to achieve the EnerFit standard, which is the passive house retrofit standard. We did achieve that, and we actually got very close to passive house metrics at the end of the day. As you can see, all the foliage, vines growing up. There's our wood for the fireplace. And it's a pretty traditional main cape. Cedar shakes, corner boards, lots of foliage, lots of humidity issues. This is a complicated geometry, much more so than the Knox house. And as you can see, we still have our 1970s antenna on the roof of the house. These are a little bit hard to read, but these are primarily the beginning metrics for this house. We were using about 1,100 to 1,200 gallons of oil a year for heating and domestic hot water. We were spending, a lot of money heating this house. We had an energy audit done by a third-party verification. I had already blower door tested the house, but I wanted to see what Topher and Paul came up with. And here's some other heating and cooling metrics, which really not that important. Electricity usage, domestic hot water, et cetera, et cetera. I have 2 young kids, 2 dogs, 15 fish, and we use a lot of domestic hot water. We do laundry constantly. By we, I mean my wife. So much and there's a trade-off there because I never know where my clothes are. She puts them away in a different spot every time, keeping things spicy. 1,100 to 1,200 gallons a year for oil. Number 2, heating oil. That's maintaining an interior average temperature of about 62 degrees in the winter time. So it was not the most comfortable house. I'd be at my desk with my hoodie on, typing like this at 10 o'clock at night. We'd have the fireplace going, the baseboard heat ripping, and we were all still freezing. Domestic hot water usage, I'll come back to this. So the assemblies before the retrofit, the walls were basically an R14 wall, 2x4 exterior load-bearing wall, fiberglass back insulation, which we chose not to replace.